Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you find the content useful, interesting, please consider liking, commenting, sharing, and most importantly, subscribing to our channel. We're very small at this point. We'd love to be able to grow, and with your help, with any sort of interaction that you can give our channel and our videos, we would greatly appreciate it. What I want to talk about in this video is a very weird result that comes up in a Calc 2 class when you start talking about the idea of an infinite series. It's called the Riemann's rearrangement theorem. So let's see what this is all about. First and foremost, when is addition of real numbers commutative? Well, there's two primary cases. One, if I have a finite sum, of course, 1 plus 4 plus 6, I can take those terms, I can rearrange them. 6 plus 1 plus 4 equals 11, right? We're all familiar that addition of real numbers is commutative. And when we say that, we're always thinking of the finite case. It's also true for an absolutely convergent series. In other words, if I take the sum of 1 over 2 to the n, which is, a geometric series with the r value equal to a half, that's convergent, which is, of course, is 1 plus a half plus a quarter plus an eighth, etc. And we can show that that's equal to 2, again, thinking of this as a geometric series. What I can do is I can take these terms and I can jumble them up. In other words, I can take a quarter and then plus 1 and then plus a 16th and then plus an eighth and then just take those terms, I can reorder them, and it's still going to add up to 2, which seems pretty reasonable. If the sum is 2, then if I just add them in a different order, then the sum is 2 again. Here's where it gets weird. Consider the alternating harmonic series, which in this case turns out to be a conditionally convergent series. We know this diverges if I take the absolute value of it, because then it becomes the harmonic series, so the sum of 1 over n, and there's various tests that we can show that diverges. But if I take this as an alternating series, then remember that as long as this term converges to 0, then this does actually converge. But it only converges conditionally. It has to have the alternating portion to it. The series is 1 minus a half plus a third minus a quarter plus a fifth minus, in other words, the terms are alternating signs. What I want to do is I want to take these terms right here, and let's kind of do one of these ideas. Let's reorder them, and let's see what happens. If I take, let's say, the sum 1 plus a third plus a fifth, so I take this term, and this term, that equals 1.53 repeating. Then if I take the first negative term there, and I subtract the half, I get 1.03 repeating. And then I take all those terms, and then I add 1/7 through 1/15, all those positive terms, which again, I'm just kind of plucking off those positive terms. This equals 1.52. Then I could subtract, the 1/4, bringing it down to 1.27, and then I could add more positive terms. In other words, what I can do is I can add terms to get up above 1.5, and then I could subtract a term to get, below that, and then I'm going to add positive terms to get back up just above 1.5, and then I'll subtract, and I'll just keep doing that, and these partial sums are actually going to converge to 1.5. In other words, I can take this infinite series, I can rearrange the terms so that the sum of all of those terms will be 1.5. Now, what I can also do is, let's look at a different combination. What if I just take 1 plus a third, and I start there, which is 1.3 repeating. Then I subtract a half from those terms, get that down to 0.83. Then let's add a bunch of positive terms to get that back up above 1.25. Then I could subtract, add, and all of these partial sums are actually going to converge to 1.25. So therefore, the entire sum of terms, I can rearrange them to make them equal 1.5 or 1.25, or quite frankly, any other real number I want. That is a very weird result. And again, this shows that in the situation for an alternating harmonic series, which does converge, addition is not commutative. Okay. And again, this is actually true for any alternating or any conditionally convergent series. If I have a bunch of positive terms, negative terms, so infinitely many, and it does converge, but not absolutely. If it's absolutely convergent, then I can't rearrange them to get a different value. But if it's conditionally convergent, strictly conditionally convergent, so it's not also absolutely convergent, then I can rearrange the terms to make them add up to any real number. Thank you for watching. Don't forget to subscribe.